think about the present value of an annuity formula. So you see that present value equals to payment multiplied by this annuity discount factor. So when n goes to say 100, 1,000, 10,000 till infinity, then this annuity discount factor is pushed to a limit of 1 over I. So when that's the case, when n goes to infinity or say goes to forever, then the present value is payment multiplied by 1 over I, or say payment divided by I. And for that, we call it the present value of perpetuity. So what is a perpetuity? A perpetuity is a special type of annuity in which the cash flows go 1 year after another year till forever, or say infinity. So an example of perpetuity is a preferred stock. They promise to pay fixed amount of preferred dividends forever, or say indefinitely, without any maturity. So when that's the case, we say it's a perpetuity, and the present value of this perpetuity is using a simple equation that is amount of payment divided by the interest rate. So if we want to find the present value of a perpetuity that pays $100 per year forever, or say year after year, and the discount rate, or say the interest rate is 10%, we use the 10%, 100 divided by 10%, so the present value of this whole infinite annuity, or say the perpetuity, is simply $1,000. Next, we want to talk about how compounding frequency affects the present value and future value of multiple cash flows. So all our previous examples have used annual payments and annual compounding or discounting. But many business or personal situations require more frequent time period than simple yearly entries. So if you actually look at your credit card statements, you may notice that they always stay daily compounding. So daily compounding is just an example of more frequent compounding. By more frequent, we mean more frequent than once a year. So let's talk about the implication of compounding more than once a year. If we look at the two timelines here, the first timeline represents $100 compounding annually by a 10% annual interest rate. So after 3 years, the future value of this $100 will be 133. So this is what we did in chapter 4, nothing really new here. But if we follow the so-called semi-annual compounding for the same $100 in 3 years, when we use semi-annual compounding, or say twice a year, then the whole 3 years means 6 times of compounding. 6 is 3 multiplied by 2. And we will use a 5% interest rate, 5% semi-annual interest rate. Where is the 5% coming from? If for the whole year it's 10%, then every 6 months you will use 5%, which is half of the 10%. So 5% compound 6 times, and the future value result will be 134.01. So this result is a little bit different, or say higher than 133.10 from the annual compounding. So you get the idea that when we use more frequent compounding, we end up with different future value. We actually end up with higher amount of future value. So let's look at some terms. Nominal rate, or say I-norm, this sometimes is also called quoted or stated interest rate. So this is the interest rate usually stated in the contracts. If we say 8% quarterly, that does not mean 8% each quarter. This means 8% annual nominal interest rate, and then you compound quarterly. 8% daily, again, this doesn't mean 8% every day. It means 8% stated or normal interest rate for the whole year, but then you use daily compounding. Okay, so if we use nominal interest rate divided by the number of compounding periods each year, then we have the interest rate of each period. So the IPER, that is the interest rate of each period. So for example, if M equals to 4, so 4 times a year, that means quarterly compounding. Then each quarter, the quarterly interest rate is the annual interest rate divided by 4. If M equals to 12, then we have monthly compounding, 12 times a year. Then the monthly interest rate is the annual nominal interest rate divided by 12. So that's why we say if the annual interest rate is 12%, then each month the interest rate will be 12% divided by 12, which is 1% per month. So when we say 12% monthly, it doesn't mean 12% every month. It means 12% for the whole year and then 1% each month. So now, for example 5-5 in your book, if you want to buy a car and you want to pay about $500 per month for a car, and how much can you borrow if the interest rate at 9% and you pay the loan over 4 years? Well, you don't pay year by year. Since you are actually paying month by month, we are treating this as a monthly compounding problem. So when you have 9% for the whole year, then each month you have 0.75% interest rate. So that's why you see 0.0075 or say 0.75%, 1 plus I, and then at the power of 48. 48 means 48 monthly payment within 4 years, because there are 12 payments each year. So 0.75% as the interest rate, 48 payments, each payment being $500. That means the total present value of this annuity is $20,000, a little bit more than $20,000. So that is the present value, or what you can afford to borrow if you can pay $500 each month under a 9% annual interest rate in 4 years. So again, you treat this problem as a monthly compounding problem instead of an annual compounding problem, because you are making monthly payments. You don't really make your car payment once a year, right? If you want to watch the video about how to solve this question, you can click on these links provided. The specific link to solve the problem using your own calculator is also provided here. Now, looking at another example, if you, instead of contribute $4,500 per year for 40 years, if you actually get to contribute monthly. So let's just say if the goal is $4,500 per year, so each month you divide $4,500 by 12, right? That's your monthly contribution. And 7% per year annual return, then monthly it will be 7% divided by 12. So let's take a look at future value calculation. This formula is still the same future value calculation formula. The only difference now is, instead of using annual interest rate, now you are using monthly interest rate. Instead of using number of years, now you are using number of months. And each payment is not $4,500 anymore, it's $375 per month. So 375 multiplied by this compounding factor, and it turns out you can have about a little bit lower than $1 million. Okay, so remember before in the previous example, when we calculate the future value based on annual contribution, the future value was this much, and now under monthly contribution, the future value actually is a little bit higher. So probably by now you already get the idea that more frequent compounding, the higher future value you can end up with. Well, again, these are links to the videos that help you better understand how to work on these questions. Another compounding, frequent compounding question example. If you are finally ready to retire with a nest egg of $800,000, this is the amount of money you would have by the time you're going to retire. And you're going to invest this much money in the mix of stocks and bonds that would allow you to withdraw $8,000 per month for 30 years. $8,000 per month for 30 years, that is $360 payments, right? So what interest rate do you need to earn? So the question is, if I'm putting this much money, this is what I would already have, and then I'm putting this money in the account and hope to get a return, generate a return each every month from this account, and hopefully that can afford a withdrawal of $6,000 per month for 30 years, or say for 360 months. So we have N is 360, which is 30 multiplied by 12. Present value is this much. This is what you would already have by the time that you start your retirement, and payment will be $6,000. You notice that between present value and payment, one positive, one negative. Okay, it doesn't matter which one is positive, which one is negative, but between these two numbers, one should be positive and then the other should be negative. Okay, and future value will be 0. This means after 360 payments, your account will be depleted and now nothing, or say $0 left. So if that's the case, what is the return that can help you withdraw, or say afford your withdrawal of $6,000 of 30 years? So when you can compute for IY, the result is 0.680. So that is 0.680% from your calculator, and that, based on your setting, is a monthly interest rate. So then you want to convert it to an annual figure, and you simply use this percentage number multiplied by 12, because this number is per month. Then for 12 months, you multiply by 12, and that means your APR, which is annual percentage return, is about 8.23%. So if you get to invest all your $800,000 in an account that generates a 8.23% annual return, which is also about 0.686% every month, and then you can actually withdraw $6,000 each month from that account, month after month, for 30 years. So that is a typical retirement planning question. The links to the videos are provided here. If you're interested, go to watch those videos that explain how to work on these questions. The compounding frequency questions we walked so far actually help us to understand this concept, which is called effective annual rate, because you got the idea that when we use more frequent compounding, we end up with higher amount of future value. That means the actual return we realize from more frequent compounding is actually higher than the nominal or stated annual interest rate that we are quoted, or say that's stated in our contract. So that's why we need to know what is the actual or the effective annual return from the more frequent compounding. The formula is given here. So it says if we have more frequent compounding, say m times a year, then the actual or say effective annual interest rate is simply 1 plus the nominal interest rate divided by m. Remember, for example, if m is 12, then this gives you the monthly interest rate. And then you compound for m times in a year. So again, for example, if it's monthly compounding, since we have 12 months in a year, then you compound 12 times within a year, and then you use this result minus 1, and that give you a so-called effective or equivalent annual rate, EAR, or sometimes EFF. Okay, so if you have a nominal interest rate of 10% per year, but you get to do semi-annual compounding, or say twice a year, then every 6 months you have actually a 5% interest rate, and you use the 5% interest rate to compound twice in a year, and use this result minus 1, you get 10.25%. This is actually different, or say higher than the 10% quoted interest rate. So what does that mean? It actually means 10.25% annual interest rate is equivalent than 10% annual interest rate compounded semi-annually. So why is it important to consider effective rate of return, or say the EFF? Because investments with different compounding intervals or frequencies provide different actual or effective returns. So we need to look at the EFF to understand the actual return. And we are now looking at a series of numbers to see how compounding frequency actually affects the actual return that we are realizing. So if the annual interest is 10%, of course, then based on annual compounding, the effective return is the same as 10%. But if we get to do quarterly compounding, then the effective rate is 10.38, which is higher than 10%. If we get to do monthly compounding based on the same 10% nominal rate, the effective rate will be 10.47. And if we get to do daily compounding, the effective rate will be 10.52%. So the higher frequency you have, or say the more frequent compounding you get to have, the higher effective rate you are realizing. And by the way, you may want to practice using the effective annual rate formula based on 10% annual return and then quarterly or monthly or daily compounding, and see if you can get the results by yourself. And again, bottom line is you need to understand that more frequent compounding, the higher effective annual rate. And maybe now you understand that why on your credit card statement they always tell you that to calculate your interest, they always use daily compounding. If we want to use our calculator to calculate the EFF instead of relying on the formula and do the manual calculation, there is function in your calculator that can convert the nominal rate to effective rate really fast. On the TI-BA2 Plus calculator, the function is iConf. You can find that from your calculator, and on the video tutorial there is a part that dedicated to using this function to calculate the effective annual rate. If you have a different calculator or TI-83, actually it would be even simpler or easier. So again, check out the video that's for TI-83 and find out how to use your calculator to calculate the EFF. So let's look at another example about the EFF. So if you are a college student, you get all those credit card offers, and if you have one card that charges 16% APR and monthly compounding, and you have another credit card that charges 15% APR and weekly compounding. And by the way, weekly, that means 52 times a year, right? So then the question is, which one has a lower effective annual rate? So for this practice question, you calculate the effective annual rate for both card offers. The first one turned out to be 17.23%. The second one turned out to be 16.74%. So you can either use the formula or use the functions in your financial calculator. Either way, you can watch the video to find out how. And I recommend you to try to get the results by yourself, and then see if your results are consistent with the results provided here. I have more practice questions here about the frequent compounding. The first question is $100, 3 years, 10% semi-annual compounding, or what if it's quarterly compounding? By now, it should be pretty simple. Same $100 present value, but you may have different interest rate because of different compounding frequency. And the first one you would compound 6 times, and the second one you would compound 12 times. And for the second question, what is the future value of a 3-year annuity? $100 annuity, that means 3 payments, each payment being $100. And the interest rate is 10% per year, but compounded semi-annually. So that question is a little bit more complicated. You can actually try different approach or different method. So the first one is you compound each cash flow on a semi-annual basis. So for example, the first 100, you compound by 5%, but instead of compound 2 years, you are compounding for 4 times. So 121.55 is actually 100 multiplied by 1 plus 5% at the power of 4. And then 110.25 here is 100 compounding by 5% at the power of 2. The 2 here is not 2 years. The 2 here is actually 2 of the 6 months. Okay, so the total future value will be 331.80. Another approach is, since you have a 3-year annuity, then you try to calculate the EFF of 5% semi-annual compounding. So it turns out to be 10.25%, and EFF is actually for the whole year. So you use this 10.25% as IY to compute the future value of this 3-year annuity, and the future value is 331.8, and this is pretty consistent with the first approach where you do it manually and compound every 6 months. So this is just a bunch of practice questions for frequent compounding, and bottom line is you need to remember that more frequent compounding, the more future value you can realize, and that means a higher effective interest rate. So you need to know how to calculate future value under different kind of compounding, and you also need to know how to calculate the effective annual rate based on the formula or using your financial calculator.